Hi everybody, we're going to get started now. I want to introduce Dr. Catherine Diamante, who is Associate Director at the Council on Science and Technology here. She's a teaching expert and PhD scientist who knows a lot more about water than I do, and so she's going to be talking about water today. I also have a little piece of swag for her.
Nice.
This rather good pin actually shows the temperature, mean global temperature from 1850 to 2019. You can download one and from any location and get mugs and earrings from Climate Central's website.
All right, awesome. I'm not going to put it on right now because I have too many microphones on me. But thank you. And I love the creativity of the data viz community related to climate data. It's been awesome to see. So thank you, Steve. I gotta get my pointer here. So as Steve said, I'm here to talk about water, and I'm a geoscientist who does a lot of research out in the western US. So here are a couple of my photos, and you really appreciate the importance of water when you're in a water scarce environment and when you're in a field site where you don't have running water and your facilities are literally a 5-gallon bucket with a toilet seat on them. So the importance of water becomes acute at that point. Let me see if this will advance. Okay. So what we're going to do today is a couple of things. So here are the learning goals. I'm a scientist, so we're going to think about the science of water, looking at scientific data and principles to explain why water scarcity exists. And we'll think a little bit about the hydrologic cycle, residence time, human water usage. We'll talk a little bit about the connections across the nexus, which is the theme of this course. So thinking about how water connects to climate, biodiversity, and agriculture. And then we'll think a little bit about trade-offs that are related to the solutions to water scarcity. I want to say from the outset that it is really critical to think about the framing of any of these lectures, and there are lots of different ways in which I could approach talking about water in the nexus, right? So we could think scientifically about how much water is there and how will that change through time. That will be a little bit of my focus, but it's just as valid to think about it from the economics. How should water be priced and who should pay? That would be something that an economist would help us with. An ethicist might help us with how we ensure equity and the distribution of clean water, which is not distributed equitably, as we'll see. And then, we could easily talk about how water impacts culture and vice versa. You think about the importance of water in so many different aspects of our society, from religious rituals like baptism to recreation to social gatherings and so on. Okay. One of the fun things about being with the Council on Science and Technology is that we do actually get to think about science in really interdisciplinary ways. And one of the things that I spend a lot of my time doing is collaborating with the University Art Museum, which has a fantastic collection. And this is one of my favorite photographs, partly because it's from a part of California near where I did my graduate work. And so I recognize this scenery quite well, but also because of the way that it is juxtaposing an agricultural scene here with an energy scene here. And this really, I want to use this to emphasize the framing part, right? Because the way that the photographer has decided to frame this image is putting those two adjacent to each other. We could just as easily look at the same place today in a slightly oblique view from the sky. Here is the power plant that we were seeing. And this is such a fantastic place because here's the nexus all coming together with the power plants here, water resources here that have been heavily impacted by a history of agriculture in the region that created canals to drain wetlands for agriculture. And it is a fantastic place to go kayaking because the biodiversity in this part of Monterey Bay, California is fabulous. So At any rate, again, just to emphasize the idea that framing is important. So what I'm going to talk about today is really from a scientist's perspective, a geoscientist's perspective. And the points that I want to make is that accessible fresh water has a really short residence time. And so that idea of residence time, to me, is important, contrasting water issues with climate issues, as we'll see. That we have enough global fresh water for human usage, but it is spread out across the earth in really different ways, right? It's not evenly distributed across the planet. And so there are places because of that that have acute water scarcity. There are also technological issues that create water scarcity. And then finally, I want to make the connection to the reading that you did for today, which is that water is related to food, and in particular, water issues and solutions are globalized through the food trade because you are trading virtual water when you are trading food, when you're exporting and importing food products. You are exporting and importing effectively the water that went into making that food. Okay. So I'm going to start off with the clicker question, just to remind you of where you've been. And I will go ahead. Can I deny that?
Yeah.
Okay. So the question is, what is the residence time of carbon dioxide in the atmosphere? And again, as I said, for me, residence time is an important framing, as we'll see. But let's just remind ourselves of what carbon dioxide does in the atmosphere. Okay. 5 more seconds. 3, 2, 1. Okay. And let's see. Okay, good. So 3/4 of you, I think, correctly identify that carbon dioxide has a really long residence time here, greater than 100 years. We're not going to agonize over how much greater than 100 years. But let me tell you why that matters, if I can get that to disappear. Okay, so why that matters is because carbon dioxide lasts long enough in the atmosphere that it becomes effectively well mixed. Right? We can look at the carbon dioxide record from Mauna Loa, and we get a pretty good measurement of what global carbon dioxide is doing. Okay, there are small variations. What do those small variations depend on? Yell out some ideas. Industry, okay, so good. That's one big thing, right? If you are close to industry, you're gonna have maybe a slightly higher value, okay? Does that matter in terms of hemispheres? Northern hemisphere, I'll do what we do in Geo 102. Does the northern hemisphere or the southern hemisphere have a higher concentration? Hold up your thumbs, northern, okay? So that's where a lot of the industry is, all right? Any other ideas? There's a hand up there. Plants, okay, so maybe there are local impacts from photosynthesis, right? Or likewise from the combustion of carbon. Yeah?
Location of carbon sinks.
Okay, so maybe some variations based on specific locations of carbon sinks, all right? But all of those are slight variations. All right. The other thing to know about the long residence time is that our emissions today will have long-term impacts, right? And so, again, just to connect back to thoughts that you've had or ideas that you've had in previous lectures, the discount rates and the ethics of whether future people matter, that's important for carbon dioxide in particular because of the long residence time. All right. I want to hammer this home. We're going to watch a video of CO2 concentrations across the globe. For those of you who were here a little early, you heard the audio of this. I apologize if it's a little loud. The audio is less important. I won't play the whole thing. But just so that you can see a model of how CO2 varies across the planet. And it's a beautiful video.
Hi, this is Bill Putnam. I'm a climate scientist at NASA's Goddard Space Flight Center. What you are looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes.
All right, so you get the idea there. It's beautiful, and I want to use this as a cautionary note about data visualization. You guys probably can't read the scale bar here, but the colors make it seem like carbon dioxide varies hugely, right? Because you have vibrant reds going down to the blues, and so this is 377 parts per million up to, I think the maximum is 390 or so, or maybe 400. It's a pretty narrow range, 395. All right, so percentage-wise, those are really subtle variations that are made quite dramatic in this visualization. Now let's look at rainfall. Okay, so rainfall is here, okay? Doesn't look like it varies as much just because of the color scheme that was chosen, but the total rainfall range here is 2,000 millimeters down to 1 millimeter, okay? Orders of magnitude. So we were talking about small percentages before, and now we're talking about orders of magnitude differences. All right, you can kind of get some sense that the water, the rainfall exists in bands, discrete geographic areas, that moves seasonally, so the months are ticking off here, and that has some impact on the biosphere, right? And that you, in particular around the equator, can see the vegetation abundance really changing as the seasonal rainfall changes. And just to hammer that home, we can zoom in on the Sahel part of Africa, and you can see again rainfall here as it comes and goes seasonally, and the impact that has on vegetation. Okay, again, water not uniform globally, right? And even within a region, it's not uniform over an entire year, depending on where you are. Okay, and that has an impact on how you use water resources. Okay, so I'm not going to make you calculate the residence time of water. Let me just assert here that it's about 10 days in the atmosphere. And 10 days is about enough time for a weather system to cross North America, okay? But it's not enough time for the air mass to mix completely through the northern hemisphere or the globe. All right, a little bit longer for surface water. Okay, what do I mean by surface water? That means ponds, lakes, rivers, water that's literally at the surface. And so what does that mean? That means that if we're going to use fresh water for drinking, for our agriculture, for our power plants, you need to find some way to keep that water around longer, because you don't want to have taps that work in the rainy season and they don't work in the dry season, right? You have to do something to manage that. Okay, so for me, the main problem when it comes to water is that you want to have enough usable water for direct human consumption, for agriculture, for ecosystems. And there's uncertainty here, right? So there's uncertainty about what climate change will do. And that's true both, as you guys have heard about, right, that annual precipitation will change, but also the distribution of that water. Even if you have the same amount of water, the storminess, the types of storm is changing, and so you might get all of that water all at once. I think there's a typhoon hitting Japan, or that just hit Japan, and they got 3 feet of water, or 3 feet of rainfall in 24 hours. Something like that, okay? If that happens, most of that water is going to run off back into the ocean, right? That's not usable water. Okay, so it matters, that distribution through time of how that water comes. There's additional uncertainty here because how big will the human population get? And I know you guys have already dealt a little bit with that when it comes to how you feed the population, and water is a huge part of that. Okay, and then the last thing is that there is a technology part of this issue. So it's not enough to just have enough water. You have to actually get the water from where it is to where people need it. And if any of you are involved in the Princeton program, Engineers Without Borders, that's one of the things that they work on in communities. They provide piping and pumps and to get water from where it is to the communities that need them. Okay. And I have to say, you know, I live about 30 miles north of here. You guys would agree New Jersey is a pretty wet place generally, and yet almost every summer we are told don't water your lawn because our system is almost at capacity. Okay, so the system is built for a certain number of people and a certain usage, and even in a wet area you can overwhelm that system without the proper technological adaptations. Okay, so let's talk about a historical example of water scarcity, and probably the one that is most commonly talked about in the history of the US is the Dust Bowl in the 1930s. And so this was caused by by a drought, right, a lack of rainfall. But again, combining not just the natural system, but the human behavior, it was also caused by poor agricultural practices that led to, you know, a huge amount of drying out of crops, and therefore no vegetation, and therefore these spectacular dust storms that blew up across much of the middle of the US. Okay, that has real financial implications. Okay, so in 1930 dollars, the estimate is $1 billion went to drought aid. Okay, 1930s dollars, so extrapolate that up to today, that's a huge amount. It founded the Soil Conservation Service, which is now the Natural Resources Conservation Service, a large agency within the Department of Agriculture that is just working on making sure that soil erosion and water is used appropriately to prevent soil erosion. There's a huge social response, so there was a big migration out of the Great Plains, and this is a really interesting time period to study if you're a social scientist. And if you are interested in critiques of art, you know, works like The Grapes of Wrath, music by Woody Guthrie and so on, the really famous photo here by Dorothea Lange, and others, you know, this was hardship leads to creativity sometimes, and this is a good example. Okay, so where did it impact? Basically, you know, a wide swath of the middle of the country. This is states impacted, and then in yellow, areas damaged by dust storms, and the most severe storm damage here in the red. Okay, so what caused that? Like I said, you know, part of it is about precipitation. So this is the Palmer Drought Severity Index, 1890 to the future here. So we're here. And you can see this big dip there, right? So that was the Dust Bowl time period. Okay. What I want to point out is that it was a big dip. No doubt about that. But there have been other times of drought, not quite as severe, but there have been other times. And so the conclusion is that the impacts were exacerbated by how our technology and our societal decisions were intersecting with the background climate situation. Okay. This is somewhat good news looking now, right? Because that means that we can make different choices and potentially have different outcomes. Okay, but it also says that, you know, our societies are sensitive to what happens with the climate system, and in particular, often that seems to be through water. Okay, and in this case, we're talking about water abundance. All right. I don't want you to agonize over this, but I do want to just point out that if you're looking at water data, you may see lots of different metrics for what is going on. I just showed you the Palmer drought severity index. I even have these grayed out because I don't really want you to memorize them. But what I do want to point out is up top that there are different types of drought depending on what you're looking at and how much you're sticking with strict natural science or how much you're bringing in social science aspects. So meteorological drought just means that you have a lack of rainfall. Soil moisture drought, which is really what rain-fed plants see. So that's rainfall, but it's also taking into account the evaporation that's happening, right? And so that's what's going to dictate soil moisture. Hydrologic drought, that one is really critical for something like the Dust Bowl, right? Because this is what is related to irrigation. What water is available for irrigation. So that's the surface water here. And then there can be socioeconomic drought. And this one you may not have thought about before, but just by the way that we are using that water, you can create scarcity. Okay? And that has nothing to do with how much it's rained in that moment and has everything to do with what we're doing with those water resources. All right. So let's now think about this. How much water is there? And if you'll excuse me, I'm going to go on a short rant because this is how it's often portrayed. And I know we've done this in this class. That if we were to take all of our water and collapse it down to a little droplet, a ball, it looks like there's not that much. And we can say 71% of the earth is covered by water, but volumetrically collapse that down, it doesn't seem that much. We can play this game too of like, okay, well, how much of that is actually usable water? So here's the percent of all the water in different reservoirs, different places where the water exists, and the vast, vast, vast majority of it, 97%, is in the oceans, right? It's salt water, and so that's, if mostly what we need is fresh water, that's not that useful, yes?
The previous slide, was that all the fresh water?
I think that was all the water, but I'm not positive about that. So I forget now if that was just fresh water. I'm gonna show you that it doesn't matter in just a moment, okay? So, you can play this game, right? 97% of the water is in the oceans. That's not that useful because it's salty. If we look at the fresh water, 77% of that is in ice caps and glaciers. Again, that's not accessible to you and me. So we start getting down to small fractions of that. And people use this to say, we don't have that much water. Okay. We're going to argue that that's probably not the right metric to use. And the reason I want to make a point of this is because when it comes to climate skeptics, they will also tell you that 300 parts per million is not very much, or 400 parts per million is not very much. And you are going to say, yes, but it is when it comes to our sensitivity to those changes in CO2. So small amounts can make a big difference. And to me, what I want you to remember is that the usable water here, groundwater and surface water, is 9 times 10 to the 24 liters. Okay, that by itself is not going to mean much to you, right? Is that a lot of water? Well, Earth is the blue planet, but that's a thin layer. Not much of that water is useful for humans. But to me, the better question is, how much water do we actually need versus how much is there, right? So I've done that math for you, so bear with me for this. So let's just think about what the US water usage rates are. Okay, and we're gonna scale that up to what the population is in 2050, or what we expect, 9 billion people. Okay, and I just said that actually just the surface water component is 10 to the 23rd liters. Okay, so what you are told ad nauseum probably is drink a lot of water. Okay, that a lot amounts to, let's say, 3 liters per person per day. That's actually a lot, 3 liters of, like, imagine a soda bottle. Okay, but nevertheless, let's say you're doing that. Let's scale that up, and if we multiply that by the 9 billion, that gets us to 10 to the 10 liters per day that we would need. Okay, that is way less than 10 to the 23rd, right? Okay, let's be more generous because you don't just use water for drinking. Okay, domestic consumption, what are things that you use for domestic consumption? What other things do you use water for in your daily lives? Showers, yes, thank you. Laundry, okay. Cooking, good. Anything else? Gardening. Okay, let's hold livestock. Is that what I heard? Okay, let's hold that one for total consumption. Okay, but unless you have your own cow that you are giving water to, let's hold that one. Toilets, flushing the toilet, right? Okay, so all of that, that should maybe horrify you a little bit, right? We are directly drinking 3 liters and 500 liters is what we use. Okay, domestically, just domestically. So again, multiply that out by 9 billion people, we're still way less than the amount of surface water that's there. Okay, total consumption. What goes into total consumption? All right, our food. So maybe we're not actually ranchers, but we're buying steaks and water went into growing that cow. All right. What else for total consumption? Industry. Okay, a lot of industry uses water to cool off machinery, to process things, maybe adding water to whatever their product is. Okay, blue jeans take a huge amount of water in processing, both for the cotton to grow the blue jeans, but also the processing of the cotton once it's grown. Anything else? Okay, energy. Okay, our power plants. You may not have thought about this, but where do power plants tend to be located? Often along rivers or coastal areas because that water is used in the power plant. Okay, many of them are steam driven. So you burn coal or natural gas that heats up water that creates steam. The steam turns turbines, right? And so you need water for the steam. You also need water to make sure that whole system doesn't overheat. Nuclear power plants, you definitely don't want them to overheat. Okay, so there's that for the total consumption. Again, we're talking 10 to the 13th versus 10 to the 23rd. Okay. So what I want you to leave with knowing is that water scarcity is a regional problem. It is not a global problem. This is both good news, right? Because if we can figure out ways to compensate for that, we can come up with solutions. This is also bad news because you can very easily be in a place like New Jersey and think, no big deal, right? Water is abundant, and so I don't have to worry about water elsewhere. And there are places in the world that really do have acute water scarcity. I would go even further than this. Water scarcity is sometimes an ephemeral problem. There are definitely dry places in the world, but there are also places that undergo the droughts that we just saw, and you need strategies to compensate for that. But it makes it a different issue than the climate issue. Okay, so let me come back to residence time. And I mentioned this at the beginning, but here's more data, right? So here's residence time of water. Atmospheric water, like I said, is about 10 days. In rivers, a little bit longer than that, 2 weeks. Lakes, let's say 10 years. The ocean, much longer than that. Groundwater can be anything from 2 weeks, so it would be here, but this is going out the maximum of 10,000 years. And ice caps, glaciers, and permafrost all the way out 1,000 to 10,000 years. Okay, so there are places where water sticks around in the landscape for longer. All right, but I want to put this to you guys now. Okay, so atmospheric water, right? Think rain, okay? So if you live in a place with variable rainfall, which is lots of places on Earth, or scarce rainfall, how do you cope with that? What do? What are some of the strategies? And what I'd like you to do is just turn to your neighbor and talk about a couple of different strategies, what happens, and then we'll have you yell out what your responses are. Okay, so you have about a minute. If they need it, yeah. All right, what do you guys think?
Oh, I just said rationing.
Okay.
Places.
Like in certain diets, like certain times of the year, we get all their like certain foods.
Okay, how might you store it? How would you store it?
I guess like create contraptions that in each household that traps the water.
Okay, like maybe rain barrels? Yeah, okay. You guys seen water towers around communities? That's a real thing that people do, absolutely. Okay, what are some of the thoughts that you had? What coping mechanisms? What do people do? Go ahead, raise your hand or yell it out. Either way, we do have microphones if you need that to be heard better. You guys did a good job of yelling earlier. Okay, what did folks talk about? Go ahead.
Reducing consumption.
Okay, so one strategy is absolutely reduce consumption. I heard a couple groups talk about this. Sometimes we talk about that as rationing. Okay, any of you guys from California? Have you had to do some of that? Right, in acute times, like I already said this actually, right? Don't water your lawn, don't wash your car except at car washes, and maybe to the point of like asking people to really limit the shower duration that you're taking or the number of showers. Absolutely. Okay, what else? Okay, desalination plants, and I put this up for a reason, right? So oceans and seas, the water there has a really long residence time. That's really handy, right? Because you can count on the water being there in the ocean. So if you are coastal, then you might be able to take that water and extract the salt from it to make it useful. I didn't put up the second point, the second question here, but let's talk about that. What is the trade-off with desalination? It takes a huge amount of energy, okay? And so there's a climate trade-off with that. All right, it's a nexus coming together. All right, what else? Desalination is only going to work in some areas and only if you have the energy to use. What else?
Long distance infrastructure.
Ooh, long distance infrastructure. So that means taking water from one place that's abundant in water and bringing it to another place. Okay? Again, you Californians may be familiar with this, with water routed from the Sierra Nevada out to the LA area, the California aqueduct. But this happens on large scales like that. The Colorado River is basically, that's the history of water in the western US, routing water from the Colorado River elsewhere. We do that on small scales too, right? How many of you guys have bottled water? Right, so you don't have to admit that. You drink bottled water. But bottled water is taking water from Poland Spring in Maine and shipping it to wherever you're going to make use of that. Okay, what else? Anything else? Okay, better agricultural practices. And I love that you raised that issue, because I'm going to point out that in a moment that most of the water that we're using is not actually the 3 liters per day that you're drinking. It's the water that you're using for the other parts of your life. And agriculture is a huge part of that. Okay? And I want you guys to really think about that, right? Because you live in California, you are told, cut down on your showers. And yet, where is most of that water being used? Almonds. Almonds, exactly. Have you guys talked about the good place in this class yet? Because you're talking about moral philosophy, and it's all about moral philosophy. And there's a character in that who thinks that he is cursed because he drank almond milk, knowing that almonds are bad for the environment, and he still drank it. I love almonds. But yeah, I mean, so a lot of that water is going to agriculture. Okay. Anything else? Water towers, water storage, and that's a huge thing that we do, okay? So we build dams, we build freshwater reservoirs in places. That is true even in water-rich places like New Jersey, there are artificial reservoirs. So what we're doing is basically finding large-scale ways to take this water and increase its residence time so that it's more like the lakes and reservoirs. We do one other thing with technology, which is we tap into that, right? Because that's water, groundwater, that is going to be a reliable source even in a dry season, okay? And so we do that. Okay, there are clear environmental trade-offs for some of these, right? So if you're taking water from this place to another, there are equity issues about where you took that water from. If you are, we talked about desalination, that's energy. If you are transporting bottled water, you're making the plastic bottles, there's energy involved in that, okay? And I want to, yeah, go ahead.
Why does groundwater have such a variable residence time?
So it depends on, groundwater is just a generic term for water that is kind of in the soil pore spaces underground. So as you might imagine, if it rains, that water seeps into the top part of the soil. It can seep back out into rivers pretty darn quickly, but if it gets deep down into the ground, then it takes a lot longer for the water to get down there, but also for it to naturally get out to other places. So it's a great question. If you are someone who is on groundwater at home, you know, wells for groundwater vary from 100 feet to 1,000 feet, depending on where the water resource is. And you may be tapping into water that is from the last ice age, depending on how deep you're going. Okay, so we do a lot technologically to kind of solve this problem. And again, I want to make the point here that that technology is not evenly distributed across the planet. Okay, so this is from the World Bank. It is a map of countries, the percentage of the population that has an improved water source. That means that they're pipes, and they're not, people aren't just dipping buckets into a stream and drinking unimproved water, but there's some improvement there. And this is a really generous description that it has to be within a 30-minute walk. Okay, so this isn't just the percent of population that has taps in their house. This is what is within a reasonably short walking distance. And yet there are vast areas, in particular in Africa, where very little of the population has that. Okay, and this is one of the things that the United Nations is working hard on to make sure that everyone around the world has access to basic water services. This is just the access to fresh water. This is not even the improved sanitary conditions, right? Do you have a toilet to go in? And so that one is even tougher. For the sake of time, I'm not going to have you do the clickers, so don't grab them. We can ask then, if you're in an area with water scarcity, what is most sensitive to this? And this is my segue into reminding you guys that 3 liters versus the 4,000 or almost 4,000 liters per day of usage, personal consumption versus more general usage, more societal usage is really, really different. Okay, and I know that you can't read this, but I'll point out, so this is a bar graph of what percentage of water, fresh water withdrawals go to different sectors of the population. This big one here is for energy, okay, thermoelectric power. Okay, that's 41% of fresh water withdrawals used for that. Okay, irrigation is 30-something percent. I can't quite read, 37, I think. So that's a huge amount of fresh water withdrawals. The public supply and domestic together is 13%. Okay, so what we are directly using is swamped by irrigation. We'll add in livestock here. That's that. Aquaculture. That's there. So that whole area is our agricultural sector. Okay. So even though there's an aspect to personal responsibility, there's a huge aspect to thinking not just about what we're directly consuming, but what societally at large we're consuming. Okay, you can think about this by calculating your water footprint. We won't do this right now, but a lot of water goes into what we are consuming. And that's not water that's just embedded within it. A kilogram of beef does not literally have 15,500 liters within it, but that's the water that's consumed in the lifespan of the cow that gave us that amount of beef. Okay. Okay. And so, one piece of advice here is you should drink tap water, eat whole unprocessed foods, and reduce your carbon footprint by buying local products. And again, I want to point out here that it's worth thinking through the trade-offs, okay? So this is reduce your carbon footprint by buying local products. If you live in a water-scarce environment, you may be also growing water-intensive crops, or you want to consume water-intensive crops, and there's a trade-off if you want to do that. And so you guys read an article about virtual water, and that virtual water is shown here, where the one approach to dealing with water scarcity is you grow the crops that you need in water-rich environments, and then you trade them, you export them, okay? And that makes a lot of sense, right? Grow almonds in places where there's enough water for almond trees, and ship that with the recognition that there's a carbon trade-off. All right, I want to say one more thing about this, which is that I think it's a really common misconception, but it's easy to make, that when we talk about the water that goes into growing that kilogram of beef, that water is destroyed. Okay, here's another way in which water is not like fossil fuels. Those fossil fuels are burned, and that becomes carbon dioxide, and that's it, right? It takes a really long time to create new fossil fuels. Because of the hydrologic cycle, a cow drinks water. What happens to it then, that water? It's not destroyed. That cow respirates. Okay, so some of that water comes out as water vapor, and it urinates, right? So that water then becomes some other form, or to put it less crassly, if you irrigate a rice field, some of that water gets consumed by the rice plant and it evaporates, but it's not destroyed. It just moves from one place to another. Okay, and so you have to really worry about where that water comes from. All right, in the last 5 minutes, I want to just cover a couple of concepts. One of the main places that comes from is groundwater. Okay, so groundwater looks like this. It is water that is within the pore spaces underground. They are not rivers of water in caverns unless you happen to be in a limestone-rich area. So it's in the cracks and between the grains of gravel. The water seeps in here and it does gradually flow out, and depending on its pathway may take a shorter amount of time or a longer amount of time. And you may have heard the term aquifer, so that's simply an area where there's usable underground water, and it's usable because there's enough water and because that water will come out of the ground easily. So it needs to have a high permeability. Okay. One of the goals for improving infrastructure in places like Africa is to make sure that local communities are drilling wells to make use of that stable water source. Okay, that's one of the quickest ways to do improvement. Okay, so this is a critical source of water in arid areas. So let's take an arid area like Saudi Arabia. Okay, so 1987, and here's what has happened to that area. And all of these little circles here that's agriculture. It's irrigated land. And I want to point out that the circles we know that that's groundwater because the way that comes is in the middle there's a well, and then there's an irrigation lever arm that just rotates around that center well pivot point. Okay, so every single one of those is well water. Okay, surface water farms tend to look like that. Just why wouldn't you do rectangles to fit all the crops in all the places you can? In a place like Kansas, again, here's the center well, and the irrigation rotates around that center. Okay, that's all well and good. You're tapping into that long-term storage. There are some problems. One of them being that if you remove that water, the little pore spaces that the water used to fill can collapse. And so it becomes not an irreversible process, right? It's like squeezing water out of your sponge and not letting your sponge come back so that it can hold water again. Okay, so that's one issue. Again, if we get intense storms, right, 3 feet of rain in Japan, that water is running off the surface. That's not going to seep into the ground. And you need gentle rainfall to get into the ground. You also need there to not be a completely paved ground surface because that doesn't allow groundwater to come in. Okay, and then recharge rates are slow. So groundwater mining is a real thing, and it's a real potential problem. And so, that's an issue out in the middle of the country. These are places where we have groundwater depletion, and I showed you the image of Kansas for a reason because that's part of the world where there's a huge amount of groundwater depletion. All right, I know that we're just about out of time. Let me just very, very quickly, if you'll bear with me for one more minute, say that the future of water is really, really tricky. We saw how ephemeral water can be. And I want to, again, emphasize the point that you can change how arid or how rainy an area is, not necessarily just by changing how much annual rainfall there is across the globe, but also those rain belts, if they're migrating through time, if you change how they move about, you can really dramatically change how much rainfall an area is getting. You can also mess with water resources if you change what used to come as snow and you make it rain instead. Because snow sticks on the landscape, longer residence time, and rain runs off. Okay, and so I hate to harp on you Californians out there, but that area, the water resources are heavily dependent on snowfall. What's happening with a warmer climate? Less snowfall, okay? And so your water resources will be harmed. Okay, the last thing, very last thing, I promise, is that there are trends in water extraction that look like they are going up. Okay, actually this is the population going up. This is water extraction here. If we look at the per capita water withdrawals, they're actually going down, okay? And so do not have this assumption that more people means more water consumption. There are lots of solutions, drip agriculture and so on, that are actually improving things dramatically. Agriculture and energy are the two main sectors that are making a difference with that. All right, thank you guys very much, and good luck with your studying.